If you are into building drones, then you might have come across autonomous flight missions. These are usually carried through programs like Mission Planner or Q Ground Control. But how do they communicate with a drone, report their orientation, or command them to a certain position? Well, this is done through the MAVLink protocol, the protocol behind all your unmanned missions. And in this video, I want to give you a basic overview of what MAVLink is, its payload format, and how to set it up on your custom flight controller to communicate with Q Ground Control. We will go over establishing a connection, reporting the orientation and system status, arming and disarming in drone, as well as selecting flight modes. So, if you are interested, then stick around. What is MAVLink exactly? Well, it stands for Micro Air Vehicle Communication Protocol. It dictates how the bytes are arranged, as well as provides a set of messages and commands. Messages involve stuff like reporting orientation, position, system health, and battery voltage. Commands, as the name implies, commands the drone to perform a certain task. This could involve giving the drone instructions to arm or disarm itself, switch flight modes, release a payload, or snap a photo. I'll get back to these in a later part. Let us look at the actual payload format. MAVLink has two versions, version 1 and 2. This is the packet format for version 1. It contains anywhere between 8 to 263 bytes. The first byte labeled as STX indicates the beginning of a MAVLink packet. Its value is 0xFE for MAVLink version 1 and 0xFD for MAVLink version 2. The second byte is labeled as len. It indicates the number of bytes present in the payload section. The third byte is the packet sequence number. It increments with every message sent and is used to detect packet loss. The fourth byte is the system ID. This is just a number between 0 and 255 that you assign to your drone or whatever vehicle it is. This is quite useful in swarm drone applications, where each drone can be identified and commanded using their respective system ID. The fifth byte is the component ID. A drone or a flight controller is made up of several components such as IMU, GPS, servos, gimbals, etc., each having their own ID called the component ID. The sixth byte is the message ID. MAVLink has tons of messages and commands, each identified with their own ID. The message ID to report orientation is 30, whereas to arm or disarm the drone is 400. Following the message ID is the payload section. It can be anywhere from 0 to 280 bytes in length, depending on the message or command. At the end is a 2-byte CRC checksum to detect data corruptions. And that is essentially how MAVLink version 1 works: simple, efficient, and widely used. However, it comes with several limitations. There is no option to verify the message source, total number of messages supported is just 255, and extending the protocol isn't very flexible. To overcome these issues, MAVLink version 2 was introduced. Here the packet length can be between 12 to 280 bytes. At first glance, the packet structure looks similar, but it has a few extra bytes in the header. First, the message field has been increased to 3 bytes, so it can have 2 to the power 24 possible messages. This adds a lot of room for improvements. 2 additional bytes have been added after the length field, called incompatibility and compatibility flag. When the compatibility flag is set to a particular value, and either the flight controller or the ground control station cannot interpret what the value means, then the entire message has to be discarded by the party that does not understand it. However, this is not the case with the compatibility flag. If it is set to a value that either the flight controller or the ground station cannot interpret, the message can still be used by simply ignoring the compatibility flag. At the end of the message are the optional 13 bytes of signature. This allows the recipient system to confirm that the message is from a trusted source. The signature contains the link ID, 6 bytes for timestamp, and another 6 bytes for the signature. When message signing is enabled, the incompatibility flag is set to 1. The message signing procedure is a bit involved, so I won't be using it in my setup. You can go through the documentation if you're interested. But now that we understand how a MAVLink packet is structured, the next important question is, what exactly are we sending inside these packets? MAVLink does not just define one fixed set of messages. Different systems like flight controller, cameras, or ground control station often need their own custom set of messages and commands. They are defined using XML files and are known as dialects. MAVLink provides 3 dialects: minimal, standard, and common. Minimal defines a single heartbeat message, along with its respective enum. On the other hand, standard adds 2 of its own messages, in addition to including the one defined in the minimal dialect. Finally, the common message set. It defines 231 messages and 167 commands, in addition to including the ones defined in the standard message set. Now there is nothing stopping you from creating your own dialect. In fact, if you wish to do so, go through the section titled MAVLink XML Schema, defining XML enums and messages, and MAVLink CRC under guides on the MAVLink documentation page. For this project, I will be using the common dialect, since it is widely adopted and ensures compatibility with existing tools. It is used by popular flight stacks like RDPilot, PX4 and INAV, as well as ground control stations like Mission Planner, QGround Control and its derivative. This means our flight control will be able to communicate with QGround Control without any modification. This is excellent, and now that we have chosen our dialect, we can proceed with creating the MAVLink library. To start with, we need to clone the MAVLink repository by following the installation guide under Getting Started tab. MAVLink offers both a command line tool called MAVGen and a graphical user interface called MAVGenerate to generate the MAVLink library from the dialects. I will be using the graphical interface to generate the libraries. Launch MAVGenerate, then select the common.xml file located in the message definitions folder's v1.0 folder. Now set the language to C, protocol version to 2.0, and then locate the folder you want to generate the libraries in and click on Generate. Once the generation is complete, we are going to see a folder structure like this. There are 3 folders here: Minimal, Standard and Common, and some extra header files. The Minimal folder contains the message defined in the minimal dialect and some supporting files. The Standard folder contains the message defined in the standard dialect, whereas the Common folder contains the messages defined in the common dialect. There are also these header files. They have more to do with MAVLink than any specific dialect. These contains functions to form a MAVLink message from incoming serial bytes, or to convert MAVLink message into bytes to store in a buffer, as well as functions to calculate the checksum and perform message signing. Let's begin using them by adding the complete MAVLink folder to our project. Since we are using the common dialect, we'll have to include the mavlink.h file from the common directory. Furthermore, in order to inform MAVLink libraries that we are not using the message signing feature, we must define the macro MAVLink no-sign packet prior to the include. This is all well and good, but how do we start communicating with the GCS? To answer this, we need to talk about microservices, specifically the Heartbeat microservice. Microservices are a well-established high-level MAVLink protocol used by both the flight controller and the GCS to ensure better interoperability. GCS and flight controller start communication by sending a heartbeat message. In most implementations, these are sent every second, so when the flight controller receives the heartbeat message from the GCS, it knows that the connection is active. Similarly, when the GCS receives the heartbeat from the FC, it learns that the connection is active. If the messages are not received for a particular time duration, the communication is considered lost. The heartbeat message has 6 fields. The type field contains the values from the MAV type enum, and it describes the vehicle or component type. That is the vehicle a quadcopter, hexacopter or a VTOL, or maybe a ground control station? Or is it a component like IMU, GPS camera or a gimbal? The list of possible values is defined in the MAV type enum. The next field is the autopilot. It is 1 byte in size and contains the value from MAV autopilot enum. It identifies the type of flight controller. Is it a PX4, RDPilot or a generic flight controller? If the message originates from a ground control station, then this field is set to MAV autopilot invalid. The next field is the base mode. It contains one of the values defined in the MAV mode flag. This tells us about the state of the flight controller. Is it autonomous mode, or is it guided through waypoints, or is it controlled through a remote? But in most cases, we set it to custom mode enabled. And this is where the next field comes into the picture, a 4 byte long custom field. When custom mode is set in the base mode, we use this field to inform the state of the flight controller, such as is it armed or in stabilized mode or in position hold mode. Following this field is the system status, which as the name implies tells us about the system state. It contains the value from MAV state enum. The last field is the MAVLink version, and it is set by the MAVLink libraries itself. So that's everything inside a heartbeat message. Now let's actually send one. MAVLink C library follows this structure, where each message or command has its own structure to configure it. For example, heartbeat messages are stored and configured using MAVLink heartbeat_t structure, whereas command long messages are stored in MAVLink command long t structure. And the entire MAVLink message including the headers, payload, and checksum is stored in the MAVLink_message t structure. Now to create a heartbeat message, we have 2 options. We can either fill out a heartbeat structure and then use a function like MAVLink message heartbeat encode to store the heartbeat object into the payload section of the MAVLink message structure object. Or we can use a function like MAVLink message heartbeat packed, which lets us set all the fields directly and packs them into the payload section of the MAVLink message structure object. I prefer the former method. To send the MAVLink message over serial, it needs to be converted into bytes and stored in a buffer. This is done through the MAVLink message to send buffer function. It takes the MAVLink message object, breaks it down into bytes and stores them into a buffer and returns the number of bytes stored. Now to implement this in code, we first create a MAVLink message object and two heartbeat objects, one to send from the flight controller and the other to store the received heartbeat from the ground control station. Just before sending the heartbeat, we configure its parameters. Autopilot field is set to MAV Autopilot Generic, type is set to quadcopter, base mode for the time being is set to test enabled, and lastly, the system status is set to standby. Now in the while loop, I wait for the previous transmission to be complete, and also if 1 second has elapsed. If this is true, then I use the heartbeat encode function to store the heartbeat object into the message structure, with the system ID set to 1 and the component ID set to autopilot 1. Next, we need to break down the message object into bytes to store in the serial buffer, and this is done through the MAVLink message to send buffer function. Finally, the message is sent through the virtual COM port. To prove that this works, I'll upload the code to my flight controller and open up QGround control. Before we hit connect, we first need to add our device to QGround control under links in the common links tab. Click on add and give it a name. Type would be serial in our case, select the serial port and leave the baud rate at the default value and hit save. Now on the main page, click on this tab and select your board. And immediately we can see the status shows not ready and the flight controller mode as test, exactly what we had set it to. If you are still not convinced, then click on Analyze tool and select MAVLink Inspector. Here we can see the messages being received from the flight controller and their parameters. And as mentioned, our heartbeat is right here. We can observe the rate it is being sent at, total number of heartbeats received, and the value of its parameters. This is all well and good, but the GCS also sends a heartbeat, so how do we receive it? Well, to do this, we first need to store the incoming serial bytes in a buffer, and then pass each byte to the MAVLink parse_char function. This function takes one byte at a time, stores them internally, and forms a MAVLink message. A return value of 1 means the message parsing was successful, and 0 means otherwise. Now with the message formed, we check its message ID, and if it is a heartbeat message, we use the function MAVLink message heartbeat decode to extract the data from the payload section and form a heartbeat message. To implement this in code, we first have to create a MAVLink status T object. This object holds the information about the state of the MAVLink channel. What are MAVLink channels? MAVLink uses this concept of channels, which are logical partitions that MAVLink uses internally to keep track of data coming from various communication ports like USB, TCP and serial ports. Suppose we have two UART ports and one USB port. We can, for example, assign channel 0 or MAVLink COM0 to the USB port, MAVLink COM1 to UART1 and MAVLink COM2 to UART2. This way we can keep track of parameters like number of messages sent, received, lost and parsing errors for each channel. In the while loop, we check if new data has arrived. If true, we calculate the number of bytes to read and then loop through the buffer while passing each byte to the MAVLink parse_char function. Next, if the parsing was successful, we use a switch case statement to check the message ID. And if it is a heartbeat message, we use the heartbeat decode function to get the heartbeat and toggle an LED on the flight controller. After uploading the code and connecting the board to QGround control, we see the heartbeat being sent from the flight controller to the GCS. And on the flight controller, we see the LED toggles. Although the toggling is quite infrequent, and this is because we have not completed the communication setup yet. In the communication setup, QGround control inquires the flight controller about the various parameters it has, supported flight modes, autopilot version, system status, system time, and if there are any pre-existing mission plans saved on the flight controller. There are other messages that it sends, such as asking for camera information or gimbal, but we can simply decline or ignore them. Let's start with the communication setup. To request the parameters, QGround control sends the param request list message. It contains the target system ID and component ID. But what even are parameters? A parameter is nothing more than a variable in your code. They contain PID values or calibration constant or any other value. They are sent as a key and value pair, where key is a human-readable, null-terminated string with 16 characters max, and the value is just the value of the variable. Now, in response to param request list, the flight controller must respond with param value message. This message is used to send the parameter's value, and it has 5 fields. Param ID contains the key, that is the null-terminated human-readable string, with a maximum length of 16 bytes. Param value contains the value of the parameter or the variable. Param type contains the value from mav param type enum, and this is used to specify the data type of the param value. Is it a float, double, or an unsigned int or a signed int, a byte or a short? The next field is param count. It specifies the total number of parameters present. Param index is the index of the parameter that is being sent, and this is the entire param value message. In addition to param value and request list, there are two other messages, param request read and param set. When the GCS wants to read a specific parameter, it sends the message param request read. It contains the target system and component ID, and the param ID and index of the parameter to be read. In response to this, the flight controller sends the param value message containing the value and index of the requested parameter. Param set is used to set the value of a parameter from the ground control station. This is quite useful when tuning PID values, since you do not have to re-upload the code with the new parameters. Param set message contains the target system and component ID along with the param ID, value and type of the parameter to be set. This is all that there is to reading and writing parameters, and all of this falls under the parameter microservice. Anyway, let's implement this in code. First, I create a param request list object to store the respective message. This is followed by 3 variables, P, I and D, and a parameters array to store the 3 variables. Next, in the while loop, after passing the message, we check if the message is param request list. After decoding the message, we check whether the request is intended for this flight controller by verifying the target system ID and target component ID. If the request is valid, we start sending the parameters one by one using the param value message. Here I send 3 parameters named P, I and D. The MAVLink message param value pack function is used to create each param value message. The arguments include the system and component ID of the flight controller, the parameter ID or name, the parameter value, the parameter type, the total number of parameters, and the index of the current parameter. In this case, 3 indicates that there are a total of 3 parameters, while 0, 1 and 2 represent the indices of the parameters P, I and D. The strings P, I and D are the parameter ID for the respective variable. Since all the parameters are of floating point type, the parameter type is set to mav param type real32. After packing each parameter message, the MAVLink message to send buffer function converts the MAVLink message structure into a byte stream that can be transmitted over serial communication. Finally, the MAVLink response to send flag is set to true, indicating that a MAVLink response is ready to be transmitted back to queue ground control. And this is done in this if statement. However, the bulk of the communication between the ground control station and the flight controller takes place using command long messages from the command protocol microservice. These messages are used when the GCS wants the flight controller to perform a certain task like arming or disarming or switching flight modes. But the thing is, the GCS does not directly send the arm disarm command or the do set mode command. Instead, it uses command long messages to do that. Suppose you want to send a letter. You would write your letter on a piece of paper and place it inside an envelope which has your address on it. The command long message is like the envelope, whereas the letter is the arm disarm message. The command protocol provides 4 messages: command int, long, ACK and cancel. The command long message has 11 fields. Target system is the ID of the system that needs to execute the command. The target component is the ID of the component in the system that needs to execute the command. Command is the ID of the command to be executed. So, if the GCS wants to arm the drone using arm disarm command, then the command field would be set to 400, which is the ID of the arm disarm command. The confirmation field increments with each retransmission of the same command. Following the confirmation field are 7 parameters field, and their value depends on the command being sent. The arm disarm command contains 2 fields. The first is called armed and the second called force. So when sending the arm disarm message, So the command long message, param1 would refer to arm field and param2 would refer to the second field, that is force. There's also a command int message, and this is used for sending positional information in param5 and 6. You can read more about the difference between the two on the command protocol documentation page. Every time a command long or int message is sent, the vehicle responds with command ACK message. This is used to inform the GCS that the command has been received. Furthermore, it informs the GCS whether the command was accepted, invalid or failed. It contains 6 fields. Command is the ID of the command that was sent through the command long message. Result contains the values from MAVResult enum and specifies whether the command was accepted, invalid, unsupported, failed or is it in progress. The next field is progress. When the result is set to MAVResult in progress, then this field is used to indicate the progress in percentage. Result param2 is used for additional information and should be set to 0 when unused. Target system and component ID is the ID of the system and the component this message is sent to. In this case, the system and component ID would be that of the GCS, as the message is being sent from the vehicle to the GCS. At last is the command cancel message. This is used to cancel the execution of an ongoing command. Although, this message is a work in progress and should not be used in stable products. We have now covered the command protocol, but occasionally the GCS needs to ask the vehicle for a specific message, like the system status, autopilot version or the supported flight modes. To do this, the GCS sends MAVCMD request message through command long message to request the particular message. MAVCMD request message has an ID of 512 and contains 7 fields. The first field contains the message ID of the message to be requested. Following it are 5 parameter fields similar to that of command long message. Suppose the GCS requests the available flight modes. The command ID field in command long message would be set to 512 for MAVCMD request message, and the param1 field would be set to 435. The value of param1 field in the command long message maps to the first field, that is the message ID field of MAVCMD request message, and the ID of the available modes message is 435. In response to this, the vehicle sends a command ACK message followed by the available modes message. There are well over 200 messages, and I do not intend to cover every single one of them. But understanding the ones we just covered will prepare you to handle the rest. With that said, let's implement this in code and complete the communication setup. Here is the code. I have created 2 new objects, system status and current mode, to store the system status and current flight mode respectively. Next, we have 3 arrays to store the flight, middleware and OS custom version, whose values are set at random. These arrays will be used in the autopilot version message. To decode and create a MAVLink response, the handle MAVLink message function has been created. Just before entering the while loop, we initialize the system status object. This message has 16 fields, however, we are only concerned with the first 3 fields. They are all 32-bit long bitmap containing the values from MAVC's status sensor enum. Onboard control sensor present tells the GCS what sensors are present on the vehicle. Onboard control sensor enabled tells the GCS which sensors are enabled out of the ones present on the vehicle. Onboard control sensor health tells the GCS whether the sensors are faulty or healthy. A value of 0 means error and 1 means healthy. Load specifies the usage time and will be set to 1. Since we do not have a voltage and current sensor, the battery voltage is set to uint16 max, while the battery current and remaining capacity are set to -1. The remaining parameters are all set to 0. Next is the current mode object. It contains 3 fields. Standard mode is set to custom mode enabled, same as the base mode field on the heartbeat object. Custom mode and intended custom mode are both set to position hold. Now, in the while loop, after passing the message, we call the handle MAVLink message function. This function is a bit long, but we'll start with the request message part. If the requested message is one of the 3 listed here, we set the message ID to param1 of command long message and use a goto statement to branch to the start of the function. Else, we send a command ACK with the result set to MAVResult denied. If system status is requested, we first send a command ACK with the result set to accepted, followed by the system status message. For the autopilot version, we send a command ACK and use the function autopilot version pack to create the message. The autopilot version message contains 12 fields. The first field, called capabilities, is a 64-bit long bitmap and contains the value from the MAV protocol capability enum. The rest of the parameters are implementation dependent. In my case, I have assigned them random values. Finally, If the available modes message is requested, we start by checking the value of param2 field of command long message. If its value is 0, then we send all the available modes, otherwise only the requested one is sent. The available mode message contains 6 fields. Number modes is the total number of modes present. In my case it is 4. Mode index is the index of the mode that is being sent. The standard mode field contains the value from MAV standard mode enum, which contains a list of common flight modes. Custom mode is used to set autopilot specific flags. Although for things to work correctly, it needs to be set to the same value as mode index. The properties field contains the value from MAV mode property. It is used to specify if the selected mode is advanced, not user selectable, or is controlled automatically. Mode name contains the name of the flight mode, and is used when the standard mode field is set to non-standard. This is how all of it is implemented in code. For the time being, the supported modes are position hold, land mode, altitude hold, and takeoff. At the end of the communication setup, the GCS inquires the flight controller about any pre-existing mission files using the mission request list message, to which the flight controller must respond with mission count message. It contains 5 fields. The first 2 fields are for the target system and component ID. Count is the total number of mission items. Mission type contains the value from MAV mission type enum. The last field is called the opaque ID and is set to 0 to indicate that it is not supported. Since I have not implemented mission planning yet, there are 0 mission items on the flight controller. Now to create the message, we use the function MAVLink message mission count pack. Once the GCS receives this message, it responds with a mission ACK message. To know more about missions, consider reading the mission protocol microservice documentation. And with this, we end the communication setup. So far, all the messages we have discussed were related to establishing the communication between the GCS and the flight controller. But we can also have the GCS to arm the drone and switch flight modes. To arm the drone, the GCS sends the arm disarm message using the command long message. Here we check param1 of command long message. A value of 1 means arm and 0 means disarm. If it is 1, then we set the arm flag of the base mode field in the heartbeat message and set the system status to active. Otherwise, the arm flag is unset and the system status is set to standby. To change the flight mode, the GCS sends the do set mode command. We start by checking if param1 is set to custom mode enabled. If true, we proceed to retrieve the flight mode index from param2 and assign it to custom and intended custom mode field of current mode object, as well as custom mode field of heartbeat object. Following this, we send a command ACK followed by the current mode message. For any other command sent, we send a command ACK with the result set to unsupported. Now let's upload the code and test it out. Videos like this take a lot of time to produce, and they do not get a lot of views. It is going to help me immensely if you can support my work financially. I have my PayPal link in the description and comment below. Anyway, after connecting the board and opening the MAVLink inspector, we can observe the messages and response being sent from the flight controller. Now on the home page, I can arm the drone using the slider, and the status changes to armed. From the hamburger icon on the left, I can select one of the flight modes, which then reflects in the top bar. This hamburger icon is for custom MAVLink actions and won't be present for most of you. For this to be present, we need to create a JSON file containing the command to be executed. I could not find much documentation on this, except for this one page on QGround control documentation page. But using a bit of ChatGPT, I was able to come up with this. And I need to mention that I have no clue about JSON syntax. Version and file type are set to the exact values as shown on the documentation page. Actions contain the command ID and the value for its respective parameter. Label contains the string, which is displayed as the button text on the fly view page. Description is the description for the command. Since we want to set the flight mode, mavcmd do set mode command must be used. Therefore, the mavcmd field is set to 176, which is the ID of the do set mode command. Param1 of do set mode command is set to 1 for custom mode enabled. Param2 is set to the mode index of the flight mode from 1 to 4 for the respective flight modes. Parameters which are not specified will default to 0. And this is all that there is to it. For QGround control to utilize this file, it must be saved on the following directory depending on your operating system. Now under MAVLink Actions on the Fly View tab, select the flight mode file. Restart QGC and connect the flight controller. Your MAVLink Actions icon with the flight mode now appears. Great. Now the last point that I want to cover in this video is reporting orientation, altitude and position. To report the orientation, we have two messages, attitude if you are using Euler angles and attitude quaternion if you are using quaternions. I'll use the latter since quaternions are what I'm using to represent the orientation. Time boot ms is the time in milliseconds since boot. Q1, Q2, Q3 and Q4 are the 4 terms of the quaternion. Roll pitch and yaw speed are the angular speed in radians per second. The last parameter is left at 0. To report the position, we have global position int message. This can also be used to report the altitude. But since I do not have a GPS, I'll use a separate message called altitude to report the altitude. The first parameter is the Unix epoch or system time since boot in microseconds. Altitude monotonic is the altitude measured at boot. Altitude AMSL is the altitude above sea level. Local altitude is the altitude in the local coordinate. I set it to the same value as AMSL. Altitude relative is the altitude above home position. Terrain is the altitude above terrain, and bottom clearance is the clear space under the vehicle. Set them to -1001 and -1 respectively to indicate that they are not present. Now to implement this in code, I first had to include the drivers for the IMU and barometer, along with the EKF for orientation and altitude estimation. Following this, the peripherals are initialized. And in the while loop, I use the function MAVLink message attitude quaternion pack to create the attitude quaternion message, which is then sent at a frequency of 25 Hz. For altitude, the function MAVLink message altitude pack is used to create the message, which is then sent at a frequency of 10 Hz. One thing to keep in mind is that we do not want to send these messages right after connecting to Q ground control. Instead, we must wait to receive the mission ACK message from the GCS. My code is a spaghetti, but I'll upload it to GitHub anyways, so you guys can use it as a reference. Now let's proceed to test it out. With the code uploaded and the flight controller connected to the GCS, I waited for the communication setup to complete, following which the flight controller started reporting its orientation and altitude. Ground control stations are mostly used to carry out autonomous operations. To carry these out, the mission plan protocol microservice is used. I really wanted to explore and cover this topic in this video, but I am running low on time as my examinations are starting in a few days, so I must leave that for a future video. Although I must mention that the mission protocol is a mix of parameter and command line protocol. So if you understand it too, then implementing mission planning would not pose much of a challenge. Anyway, thank you for watching this video, and in my next video we'll look at creating firmware for this flight controller using FreeRTOS.